Good afternoon, thank you for joining us. Today we'll be presenting our project, which is called the EBike. This project is presented by Joseph, Joel, Zachary, and myself, Thomas. In our Q4S, we introduce a new personalized and augmented P&B approach. Through this project, we hope to prove that our P&B approach would work in a real-world design situation. Additionally, this project allowed us to gain some of the learning goals set forth by some of our group members in the early assignments. These included, but were not limited to, the ability to evaluate solutions to a problem, the ability to identify users' needs, as well as the ability to come up with ideas individually and in a group. Our augmented and personalized P&B approach appears on the figure shown here. Although we could go through all the modifications, this would be tedious, and this was more the Q4S than the project itself. But some of the most important augmentations that we feel like we should mention are the ability to identify appropriate talent source and work personnel, to set up collaboration infrastructure, and finally to compile, identify, refine, and extend a customer's requirements list. Additionally, the possible environmental impact of the creation of the product was taken into account. This is going to be talked a little bit in this presentation, but it goes more in depth in the total assignment that we're handing in.
So after we selected our project of designing a new e-bike, we moved to the first step of the Pollen Bites process, the planning and task clarification. Before we proceeded with the design problem itself, we needed to know what our time was like. Our project and our team had some significant overlap with ME6105, so we assembled all of the deadlines for both classes into one Gantt chart. Within that framework, we set goals and made plans for design milestones that we would reach in order to meet our overall deadline. We also needed to understand how to best use another resource, our team members. We compared the skill levels and specialties of each team member and discussed who would do what portions of each task, with each team member focusing on his greatest strengths. Having done this, our modified P&B also called for us to define the tools we would use for collaboration. After a brief attempt at emailing files back and forth, we decided to set up a Dropbox folder to enable fast, up-to-date file sharing and efficient collaboration.
We assumed an organizational situation where we were approached to design an electric bike for commuting in an urban environment. This bike would be specifically aimed at college students. The next step was to create an influence diagram, seen here, and a means diagram, seen here. From these two diagrams, we were able to conclude that the most important attributes for the customer would be range, mass, and climbing ability. The next step was to analyze the demand. This was done through a survey, which was completed by approximately 100 to 120 people. In it, they were asked how much they would be willing to pay for a bike with a certain range, max grade in degrees, and weight in pounds. This enabled us to link specific characteristic to customer demand and ultimately to utility and profit. The resulting graphs are shown here. Additionally, when analyzing market, we took a look at current regulations applicable to e-bike law. Some of the constraints which we noted included a 750 watt power input by the motor, as well as a 20 mile per hour speed limit. Now that we had an idea of what the market was, we are ready to move on to the customer requirements list, which is this part. Using the totality of our research, survey responses, as well as other analytical tools, we were able to come up with the following requirement list shown here. These including wishes and demands of the customer. Please note that the requirement list was split up in different sections, including general safety requirements, electrical features, customization and visual appeals, features, performance attributes, failure attributes, and finally, material attributes.
With the requirements list in place, we could move on to the next step, developing a principal solution. Because our goal was to create an updated e-bike, our solution space had some very clear boundaries from the beginning. We did not, for instance, need to compare the merits of wheels with the merits of skis. We did have to look at functions that would be performed by the product within the context of e-bikes. You can see these organized in this function tree. Similarly, we organized the design objectives into this objectives tree. The interplay of these functions and the optimization for our target market is what sets our e-bike apart from existing products. Predictably, the objectives we had identified had some serious conflicts. One objective was to assist the rider over difficult terrain. The function structures and working principles associated with this are the components of the drivetrain, and one efficient and reliable drivetrain is based on the chain and derailleur. Another objective was to allow for trousers and skirts. Unfortunately, a bike chain tends to stain riders' clothing with grease, and the sprockets and chain rings can rip through clothing and skin alike. A third objective was easy to maintain, and bike chain maintenance is very simple, but it must be done with some frequency, thus competing with the objective long maintenance intervals. Two overarching themes at this stage of the design process were risk assessment and the identification of cultural influences on the design. For instance, using an unguarded chainring on a bike leads to the risk of shark bite, where the rider's shin is injured by the chainring in a crash. This risk was unacceptable for our design. Similarly, one efficient and comfortable bicycle design is the recumbent. Cultural analysis reminds us that cyclists in the US need to share roads with SUVs and other tall vehicles, and so risk assessment makes an upright seating position necessary for the rider to see and be seen. Balancing these objectives took several iterations of morph chart and evaluation matrix. We initially settled on a fully enclosed chain with an internal hub gearing. We moved forward with the design process, but soon returned and re-evaluated our decision. A few more iterations brought us to the realization that we were ignoring our greatest strength, the combination of electric input with rider input. This led us to our principal solution. We elected to use a fully enclosed drive shaft with a single speed. The electric motor enables the rider to overcome the lack of lower gears, and the entire system is simplified and thus made more reliable. As an added bonus, simplifying the system enables the individual parts to be replaced without scrapping larger portions of the bike, thus helping our environmental goals as well.
With the principal solution selected, the stages of embodiment design may begin. The initial development of the construction structure begins by defining the relative positions of each of the components on the electric bike. Beginning with the dimensions from an industry current bike, a parametric CAD model was generated to aid in the development of a product family of bikes. Parametrically defining the bike's key dimensions at this stage enabled rapid changes and linked updates through the definitive layout development. Nearly every component of the bike was given a rough 3D model at this stage, with the frame being shown as a typical example. Concurrently, a drivetrain simulation model was developed using the Modelica language in Daimola. At a very high level, this model consisted of the combined weight and power input of the rider and his bike, air resistance, gravitational effects of the terrain, and the stored energy in the battery. At this stage, the individual components were defined and assembled into a single bike model that was run using varying input parameters to validate the correctness of the model. This model will go on to be used for more advanced simulations and optimization of the bike. These initial layouts were evaluated against economic criteria through cost estimating individual components. Cost models for the motor, frame, and battery were developed by fitting curves or surfaces through a sampling of current component prices. Combining this data with the consumer demand model previously identified will be an integral process while optimizing the design. The bike's preliminary layout is now defined as much as possible at this stage. Most of the components have defined relative positions. By linking the CAD files to a single spreadsheet defining the critical dimensions, every part can simultaneously be updated as new knowledge becomes available. The ease of dimensional changes also enables rapid development of a family of similar bikes. A few components, such as the battery, require further knowledge to decide on the placement. Several different options were proposed and will later be selected based on the new set of requirements dictated from the final optimized simulation. The Daimola model was integrated with the Model Center software in order to run many iterations with differing input conditions to optimize the model. Initially, the input parameters were compared to determine the relative effects on the output. The battery capacity was determined to have the largest impact on the bike's performance and was therefore the most important parameter to correctly adjust. As you can see, Our optimization converged to an 18.1 amp-hour battery on a 14.5 kilogram bike. This combination will yield the maximum profit based on our cost models and market demand survey results. At this stage, other special concerns were considered, such as how easily the bike can be repaired. Assembly and disassembly being a critical concern, component exploded views and 3D assembly simulations ensured that the components that would receive the most wear were capable of being removed, repaired, and replaced as easily as possible. As more details became concrete, the bike model was updated to a layout portfolio containing details for an entire product family of bikes. Each of these bikes adheres to the strict requirements determined through customer demand and utility surveys, as well as detailed performance simulations.
Our work this semester resulted in an e-bike design optimized for college students in the US, with specific focus on range, hill climbing ability, and weight of the bike, along with a commuter-friendly drivetrain design. The components are selected for ease of use, reliability, and to allow the lowest cost of repair. Some of the details of our layout are still preliminary. The next step is to complete the detailed design. Most of the components are off the shelf and can be purchased, but we would need to contact a metal fabrication shop to help us build the frame prototype. Our goal during the detailed design phase is to reduce the overall production cost to $1,298. Our analysis of the market indicates that an ideal price point for the end consumer would be $21,058.